Alright guys, so we are going to be talking about electrons and how they deal with energy. So how are they related to energy? Now, we've talked about what an atom looks like. We know that we have the nucleus in the center, and then we have the electrons that are orbiting around the nucleus. Now, why do they do that? Well, the electrons continue to orbit around the nucleus because they're attracted to it. So we need to talk about why that is. So we have the positively charged protons and the neutrons, which are neutral, located inside the center of the atom. And then you have the negative electrons that are orbiting, and they continue to do that because they're attracted. And this deals with Coulomb's law. So Coulomb's law deals with two factors. It deals with the charges of two objects and the distance that they are located away from each other. So in this formula, and you don't need to memorize this formula, it's not given to you on the reference sheet, but you just need to understand the principles that go behind it. So Q is going to be the charge. In this case, we're going to be looking at the charge of the nucleus and also the charge of the electrons. R is going to be the distance that the electrons are located from the nucleus. So basically, in Coulomb's law, if you have two objects that are charged and that are a certain distance away from each other, the closer that the objects are, the greater the force of attraction. So if it's that they're like charges, so they're both positive, they're both negative, and they're closer together, they have a force of repulsion. But if they have opposite charges, positive and negative, they will have a force of attraction. So the closer the particles are to each other, the stronger that force, and also the higher the charge, the stronger the force. So if we're talking about a positive 3 versus a positive 2, the positive 3 is going to attract more strongly. So when we're looking at the atom, and we talked about the Bohr's model last year, so when we have the electrons, they're located on different energy levels. So the closer they are to the nucleus, the lower the energy level. So when we look at electrons, and if we were to add energy to the atom itself, so we add energy to the electrons because the electrons end up absorbing it, you can cause the electrons to actually move up in energy. So they'll move from a ground state, so whatever original energy level they're normally located on, they're going to absorb energy, and then they move up in energy, so they go to an excited state. Well, what goes up must come down, so eventually the electrons will release this energy. They'll fall back to the ground energy level, and then that energy has to be released. It gets released as light or UV radiation, or sometimes IR or infrared. So as we look at the electrons in the atom and we look at the energy levels, if you see this right here, this diagram, you've got energy level 1, then you've got a huge jump to energy level 2. Then you go to energy level 3. Well, it's not the same as the jump from 1 to 2. And then as we get higher and higher in energy, those energy levels actually start to converge, meaning they get closer and closer together. Energy level 5 is still going to be higher than 4. Energy level 6 is still going to be higher than 5, but the difference between the energy level gets smaller and smaller. So when I'm looking at this, if I'm looking at the electrons moving from an excited state back to a ground state, the highest amount of energy that you would see, the biggest difference, is actually going to be from energy level 5 to 1. But if I'm looking at 5 to 4, that energy level is not going, or that difference is not going to be as great as from energy level 2 to 1. So electrons are normally going to be found on their lowest energy state, that's ground. If you add energy, they move up in energy, and they go to an excited state, so they'll go up in energy levels. The electron will then release that energy, it falls back to the ground state, and that energy usually gets released as light, or it could be UV or IR energy. So if we're looking at these, well, the biggest jump from all of these transitions right here would be from 5 to 1. If we're looking at the least, though, when we're comparing all of these jumps, it would actually be from 4 to 3. So just know that when we're looking at energy levels, as we go out further away from the nucleus, they will increase in energy, but that difference becomes smaller and smaller as we go up in energy levels. All right, so we're talking about energy, and energy, when we talk about energy, we have to talk about the wavelength and the frequency of that wave. So when we're looking at the wavelength, that's just going to be the distance of the wave. So from crest to crest, you could also measure it from here to here. And the wavelength is going to be measured in nanometers usually when we're talking about visible light or IR or UV, but it can also be measured in meters or any really length. Now frequency is the number of waves that pass in a given second. So that's going to be measured in hertz, which is also a second to the -1, or we can say 1 over a second. Same thing. So these are all the same unit right here. So 1 over second, second to the -1, or we can say hertz. All right, so frequency and wavelength are inversely related. That means as one gets higher, the other one gets lower. So as our wavelength gets shorter and shorter, the frequency at which the waves pass in a given second gets higher and higher. So if it's longer, you have a lower frequency. So now if I were to take the wavelength of any wave and multiply it by its frequency, I'm going to get the speed of light, which is a constant. It's always that value. It's 3.0 times 10 to the 8th meters per second. So this applies for all types of electromagnetic radiation. They all travel with the same speed in a vacuum. So they all travel at 3.0 times 10 to the 8th meters per second. So if I want to figure out the frequency or the wavelength when I'm given one of these variables, I can use this equation. So when I'm looking at this problem right here, it says calculate the wavelength. So we're looking for wavelength. And we were given frequency. So that's 60 hertz, which remember is just the same thing as seconds to the -1. Well, we have this equation. So basically we can just plug it into that equation. So my speed of light is constant, which is this. And my wavelength is unknown. My frequency is 60. So if I want to get my wavelength, just simply divide by 60. And then this is how our seconds will get canceled, because remember, hertz is seconds to the -1st. So our wavelength here is going to be equal to, so it's 5.0 times 10 to the 6 meters. All right, so let's look at the other equation that we have that deals with energy. So energy and frequency are directly related, which means as one gets higher, the other one gets higher. As one gets lower, the other one gets lower. So as frequency increases, the energy of that wave will increase as well. So energy is equal to Planck's constant multiplied by frequency. And of course, C and H are given to you in the reference sheet. So I want to know, for this problem, I want to know the energy of a wave with 60 hertz. Well, I know energy is equal to H times V. I have my frequency, so I can simply plug that into the equation. So energy is equal to my constant, multiplied by my frequency, which is 60. Seconds will cancel. And my energy would be equal to 4.0 times 10 to the -32 joules. All right, so let's look at something else. All right, so calculate the energy of a photon that has a wavelength of 2.1 times 10 to the negative 7th nanometers. Okay, so a photon is just a light particle. Remember, light can actually behave as a particle, it can also behave as a wave. So our wavelength is equal to this. And this is in nanometers. Units are important. And we're looking for energy. Well, I know that energy is equal to this. But I don't have frequency, I have wavelength. Well, I know I have another equation which does deal with my wavelength. So I can use this information to solve for frequency. So I know what this is. This is 3.0 times 10 to the 8th meters per second. And I have the wavelength in nanometers, and then I can solve for frequency, but I have to convert one of these. So 2.1 times 10 to the negative 7th meters, or nanometers, needs to be converted to meters, or I can convert the constant, either way. So nanometers on the bottom, meters on the top. Well, 1 meter is equal to 10 to the 9th nanometers. And I do suggest, you know that I don't know, I can't remember off the top of my head if that is in the reference sheet. So our wavelength is going to be equal to 2.1 times 10 to the negative 16th meters. So now plug that in to this equation. And if you saw a way to do this just by combining the two equations, that's also perfectly fine. So I solve for frequency here, and I will get this. Hertz, or seconds to the negative first. So remember, we're not done. We still have to solve for the energy here. So energy is equal to Planck's constant. Multiplied by my frequency. So my energy here is going to be equal to this, 9.46 times 10 to the negative 10th joules. All right, so now let's take a look at something a little bit different. All right, so ionization energy is the energy required to remove an electron from an atom in the gas phase. The ionization energy of gold is 890.1 kilojoules per mole. Calculate the minimum wavelength of light that will ionize gold. All right, so first thing, they give us ionization energy. So they give us energy. And it's not in joules this time, it's in kilojoules per mole. Well, what are we looking for? We're looking for the minimum wavelength that will ionize gold. So what is the wavelength required to take an electron off? And this is only talking about one electron. So this is in kilojoules per mole, okay? So when I'm looking at that, this is per mole, the wavelength is only referring to one electron, taking one of those electrons off, okay? So in order to do this problem, since I'm looking for wavelength, well, I know I'm going to have to use this equation, but I was given energy, so I'm going to have to, again, do what I did in the last problem, solve for frequency, then I can go back and look at the wavelength. But before I can even start to do that, I have to convert this, because if I look at my constant here for Planck's constant is in joules times seconds, so it's got to be in joules. And I've got to worry about this mole part, because remember, this is for a whole mole of gold. We only are concerned with one electron, ejecting that one electron off. So we're going to convert this. So this is 890.1 kilojoules per mole. Well, I know I got to convert this to joules. So that's kilojoules joules. So this is 1,000 joules is equal to 1 kilojoule. Well, now I got to worry about that mole. Well, a mole is equal to how many electrons? Well, it should be 6.02 times 10 to the 23rd electrons. All right, so I go through this, and remember, moles is on top right here. That's why we need to cancel out that mole, so the electron's on the bottom. So when I convert and do this, I'm going to get 1.47 times 10 to the negative 18th joules. And this is per electron. All right, so now I have my energy. I can go ahead and solve for the frequency. So it's 1.47, actually, that's equal to Planck's constant. Multiplied by the frequency. So now we're gonna solve for the frequency, and that's gonna be 2.23 times 10 to the 15th. And now we can go and solve for our wavelength. So C is equal to 3.0 times 10 to the 8th. All right, so now our wavelength, when we calculate that should be 1.3 times 10 to the negative 7th, and that's going to be in meters. So if you're given a problem, pay attention to the units, because that can be important. Sometimes they will give you a problem and they will also ask you to solve for the energy in kilojoules per mole. So you would have to do a conversion at the very end and take your joules and convert it in a similar fashion to this. All right, so when we look at energy and we look at waves, we need to talk about the electromagnetic spectrum. So all forms of radiation are waves, and they're on the spectrum. They have different wavelengths and frequency and energy. So it is important for you to remember the order of the waves. So radio waves will be at the end of the spectrum. Those are the longest. Then we go to microwaves, like the kind you have in a microwave. Infrared, visible light, so what you see, ultraviolet, X-rays, and then gamma. So as we go from the radio to the gamma, we will see that they get more and more energy, the wavelength gets shorter and shorter, the frequency gets higher and higher. So one way that you can memorize the order is from a saying. We can say, real men in Vegas use X-ray goggles. You can say that. There is another one that says, rabbits mate in visible, unusual, expensive gardens. Either way, however you want to remember it, just remember the order. All right.